All right, good morning, everyone. Thanks for joining us in Cheyenne. This is going to be a one-way audio stream. If you have any questions, which we encourage at the end of the presentation, please submit them through the chat window and I'll relay them to our presenters for some discussion and answers. So with that, I will turn it over.
Thank you. We're grateful for the privilege to be here today and provide an update on some preliminary evidence based on a research proposal that we submitted and received award funding for. We're grateful for Bob Budd's faith in that perhaps we could provide something meaningful and informative about the abundance of sage grouse. And this is the basic title of our presentation today. We were trying to look at the influence that climate had on the abundance of sage grouse by choosing to see if there are cyclic or non-cyclic variation patterns in these animals. The question, the take-home message is there year-to-year variation of sage grouse abundance related to climate variation? So our preliminary answer based on our research is yes and no. There is non-cyclic variation of abundance typical of the climate in the Great Basin sagebrush shrub steppe communities. But there is no abundance variation due to climate cycles. And the reason we even entertained the idea was based on the data. Here's the data for lek counts from 1948 to 2016. And you can see that for the most of the variation is recent in that sense, the up and down. But the fact is it kind of looks like there may be a trend that maybe a cyclic pattern every 20 years, for example. But one of the things we realized we had to do was, in addition to just assuming that lek counts were a reflection of abundance, we had to account for observation effort. The number of observers in 1948 through, say, the 60s or the 70s are much different than the number of observers out looking for leks in the recent history. So we took these data, all of these data, and we tried to incorporate the correction, as it were, or an adjustment for observation effort. And the way to do that was to calculate the peak males or peak male counts per lek. So regardless of how many observers there were out there, you look at the number of leks and the average peak male count per lek was a way to adjust for that observation effort. And you see that the variation declines now substantially over the same years. There is this sort of recent trend of up and down, but it doesn't really appear clear here that there's anything cyclic going on. Nonetheless, our working hypothesis, we had two. And the first is that variation in sage grouse male lek counts tracks the multi-year climate cycle in the Great Basin shrub steppe community. And the second hypothesis we worked with was that sage grouse male lek counts or the population growth rate, lambda as they're known in the vital rates community, are functions of non-cyclic climate variation. So climate cycle variation is one of the hypotheses. If there is such, we wanted to find that and track it to see if the sage grouse are doing the same thing. And second, is there any non-cyclic environmental or climate variation that these animals are using with regard to their numbers? What numbers? The first thing we wanted to do was to kind of review, and we've given this sort of background a little before. The research that Dr. Belk and I have been doing over the years was looking particularly at a fish called the Junesucker in Utah Lake. And we modeled the annual variation, cyclic and as well as random variation, due to snowfall, river discharge, lake level, and try to use these sources of variation to model the results. And we added cyclic and non-cyclic environmental variation into the vital rates of the Junesucker and used some population simulations to do that. Well, here's an example of the Provo River discharge. That's what's going into Utah Lake, and you can see the environmental variation, and it's of a cyclic nature. Those points below this line in red signify a drought condition, years in which there was just not sufficient Provo River discharge to get the young hatch of the year into Utah Lake. And the snowfall and precipitation generated this sort of cyclic trend in the Utah Lake. And we fit that using a sinusoidal function. Now, that's a big fancy word for trying to use sine functions, the typical up and down, consistent patterns in a sine function, those who remember trigonometry from high school, and try and see if some sort of function, sinusoidal function, would fit this pattern in Utah Lake. And I defined the parameters associated with the function. This, what we found, this was a significant statistical function. And looking at the data, we fit that function to the data. And this is data from 1884 all the way through 2010, I think. So, for the most part, there is a good fit for the pattern of cycles in the Utah Lake, with exception of the recent history. And there could be some agricultural, we're not really sure exactly how to explain the more recent history. But we use this information, you see, in applying it to the June sucker population. The problem was we did not have any independent estimates of June sucker numbers in Utah Lake. So instead, we incorporated climate cycle trends into a model and then simulated June sucker population growth rate over a 200-year period using matrix population model techniques, and demonstrated the likely population behavior of growth rates. So that's how we would use the cyclic information associated with the environment in which these organisms live. And we wanted to do the same thing, if we could, with sage grouse. But in the sage grouse, the good news is we have both. We have sage grouse numbers as well as measurements of climate variation, unlike the June sucker. So we were hoping that we could take rates and use them as inputs to model the response of sage grouse numbers to perhaps the cycles of environmental variation in the sagebrush community. So we calculated the growth rates based on a paper by Dahlgren in 2016 looking at sage grouse, and they calculated the total peak males for the, say, the current year, and divided it by the total peak males of the previous year. And that gives us a ratio of whether there's a substantial increase or decrease. That ratio in their estimation, that paper, became an estimation of growth rate, which seemed to match other data on vital rates for this particular organism as well. So we have the responses, the leg counts and growth rates, and then we have the predictors in the model, which are the environmental measurements, seasonal mean, max, minimum temperature, meteorological data, including precipitation or snowfall, and we also include what's called the Palmer Drought Severity Index. Some of you may be familiar with that. So to test the first hypothesis, the climate cycle hypothesis, we want to fit, as we did in the June sucker, a sinusoidal model of the annual climate trend variables in Wyoming near the major core areas. And we selected 4 major core areas that showed the largest number of peak male counts, which were the core areas E, F, G, and H. You'll see those in just a moment. And then we want to fit, then, in addition to that, those become then the predictors, X, as it were, in the model. And then the sinusoidal models trends associated with sage grouse males, or the responses, Y, for for time t. So if both of these are cyclic in nature, then we can fit this model y as a function of x and have an ability to predict then population size for a given year, for a given whatever in this particular case, the environmental variation, the cyclic components of the environment for a given year. So the population size at time t is a function, simple linear function of the environmental variation at time t. That's the idea behind that statistical model. Well, let's take a look at what the data show. Here's the precipitation measures for each of those 4 areas, E, F, G, and H. And
Do you know where those are?
Yeah, E would be Casper. E would be Lander, F would be Casper, G would be Green River, and H would be Rollins, generally.
so it's on the eastern side of the state?
No, it's spread across, and you have the G and H that are at one of them, they're on top of each other, and 2 on either side.
Yeah.
Casper and Green.
So
Basically Southwest Wyoming.
Southwest Wyoming. Okay, thank you. Then we look at, in addition to that, temperature. Now notice that there is an apparent trend, increasing trend in temperature in each of these 4. There's a lot of noise, but there appears to be an increasing trend in temperature over this period of time. We selected the period 1960 to 2016 just to in addition to stabilize the variation due to non-calibrated kinds of instructions on how to measure Lex in the first few years of the 1948 to 60. And then finally we look at the Palmer Drought Severity Index. It's almost a shotgun pattern here, right? So in looking at these, the climate cycle evidence, there just is no evidence of climate cycle trends in the meteorological data, regardless of the core areas we selected. Now, we selected these 4 because they're the top, the largest numbers, just to get an idea of what's going on. So, but the question remains, is there evidence of cyclic behavior in sage grouse abundance? If there's no cyclic behavior in the meteorological data or environmental data, is there any pattern as the LEC counts suggested in that first graphic we showed of a cyclic behavior? Well, here's what we fit sinusoidal models, and here's the typical sine wave kind of function that you would expect to be fit in each of those 4 areas, E, F, G, and H. The challenge is that some parts of it look like they might be fitting that, but other parts don't at all, as in the case of these 2 areas, F and H. But there's just a lot of variation and inconsistency in fitting these sinusoidal models. So our summary of the abundance cycle evidence in sage grouse is that there just is no reliable, meaning too much variability, in the sinusoidal fits to justify saying that there's any cyclic behavior among the mean peak males per lek. That was the way of adjusting for observation effort. And the added basis for this conclusion is just there's a lot of heterogeneity or heterogeneous estimates of cycle frequency. So if we go back, we can see that the frequency here is pretty large. There's a smaller frequency, more rapid change, right, in the amplitude. Here's one's even larger. So there's just inconsistency, a lot of heterogeneity in lack of fit in these data to those kinds of functions. So our preliminary conclusion here, looking at the data, is that there just is no cyclic behavior in this particular organism, the sage grouse and the sage grouse communities. So there's no evidence for periodic climate cycle variation, and there's very little evidence for cyclic behavior in the peak male counts themselves. So that we just conclude that there just is not, that the sage grouse are not responding to any cyclic climate patterns because they essentially don't exist. There was some suggestion of that in the behavior of the sage grouse, but just no justification for it. Let's go now to our second basic hypothesis, which is modeling leg counts versus non-cyclic environmental variation. So we use the ith, we think about algebra here, meteorological measurement, for example, the annual mean temperature, precipitation, etc. There were many of those. So we use that ith measurement of the environment for the j'th year as a predictor. So we have X subscript ij. And we use sage grouse lek numbers as a response for the j'th year. So we have Y then as a function of X. Y of the j'th year is a function of the ith measurement of the environment and for that j'th year. We fit this particular model, and we have then an opportunity to look at the range of environmental variables that are affecting the abundance of sage grouse. That's the idea. So here's an example of what's called a SPLOM, or a scatter plot matrix. It's a busy plot, but it's the first row that is of importance to us here, because we're looking at male leg counts, which is on the vertical axis. And then each of these, in this case, it's spring precipitation, summer precipitation, fall, winter, etc., and the annual average. And there is this sort of, you can't see the green points here, but there appears to be a larger center than on either end. That's for precipitation. The pattern continues, looking at, again, these references to temperature. There is a maximum temperature, fall temperature, winter temperature, etc., average annual temperature, versus the male leg counts. So if we do the third, which is the scatter plot matrix for the Palmer Drought Severity Index, we have a consistent pattern here, and that is that there is, in a middle or moderate sorts of responses, whether it's precipitation temperature or the drought severity index, there is a higher leg counts in the moderate ranges of these environmental variables. And you can see all the correlation that's existing here. The fall PDSI is highly correlated with the summer PDSI. The same is true with precipitation and temperature, but those you would expect. It's this particular row of that matrix that's of value to us. So looking at that, just backing up briefly to temperature, you can see here that, just look at this plot. This is the, what is that? Spring versus summer. And you notice that the colors reflect the E, F, G, and H areas. There is some separation between areas associated with those functions. So the thought is there any real differences between, is a core area, if you've seen one, you've seen them all, or are they significantly different? So we choose to use a method in statistics, a multivariate method called discriminant function analysis. And it takes, in this case, 6 variables. There's a 6-dimensional kind of response, which includes these variables, population growth, total peak male counts, and then the environmental variables. And it summarizes all that multidimensional information into 2 new variables. This one, canonical variable 1 and canonical variable 2, that is designed to maximize the discrimination between the groups if it exists. Well, this sort of suggests that there is a way very easily to tell, certainly, G from H. They're disparate with regard to the information in these variables. But E and F are almost on top of each other. In other words, E and F are very similar in their the population of sage grouse and how they're responding to the environment. But these two are disparate from G and H. So there is some evidence that there are differences among the core areas themselves and how the sage grouse are responding to their environments.
So Tom, again, E and F are Casper and Lander, G and H are Green River and Rollins.
Yeah, and those correspond to the local working group areas.
Yeah. Okay.
Good. Okay, so let's look at the strongest model fits to this second hypothesis, the idea of looking at non-cyclic variation, or that the data on males per lek as a function of a particular environmental variable. Now notice that we chose to take the logarithm of that number of males, because if you look back at these scatter plot matrices, there is an order of magnitude difference. Here's up to 200, everything else is down here maybe at 10 or lower. So there's an order of magnitude difference in the responses that typically can be modeled as a logarithm, or if it's normally distributed, typical bell-shaped curve, it's the bell-shaped curve is in the logarithms of the data and not the data themselves. But that still allows us to do the idea of prediction. And notice that we have larger responses in terms of the larger number of males per lek at low precipitation, and as precipitation increases, those years with large precipitation, you generally have lower population numbers, lek numbers. The same is true with temperature. There strictly are negative relationships. But in this particular case, the strongest relationship was between fall, I'll get it right here, the fall precipitation and the logarithm of male lek numbers, and summer average temperature. So the fall average precipitation and the summer average temperature, those two were the strongest in relating these sage grouse numbers. So high temperatures and high precipitation generally not good for looking at the expected number of males per lek in those years. But here's probably the most interesting relationship of the group, and that is the Palmer Drought Severity Index. In this case, it's the winter had the strongest response. They're all statistically significant, whether you choose any one particular season, but this had the strongest relationship. And notice that you have, in the Drought Severity Index, this negative numbers are associated with drought, positive numbers are associated with non-drought or wet conditions. But in both cases, the extremes, if you have drought or very wet years, the response in the log of the males per lek is smaller. It's these moderate years, or when you have intermediate non-drought and non-wet years, that you have the best response on the lekking grounds. And therefore we presume the population abundances of sage grouse as well. Well, now that we've looked at just the numbers, the sage grouse lek numbers, let's look at the actual annual growth rates as we fit these growth rates by that paper by Dahlgren 2016, Dahlgren et al. And again, we look at the numbers or the growth rates themselves for each of these four areas, E, F, G, and H. And there's some evidence of the up and down. Is it cyclic in nature? Could we say that? Well, we look again at this scatter plot matrix of the population growth rates versus the meteorological data. Here, again, it's this first row that's of interest to us. And we have the same sort of pattern in the response of growth rate as we do in the lek numbers, total lek numbers or males per lek. And then at the moderate level, we have large responses, but on either end, it's smaller. And you can see the correlation, positive and negative, between the environmental variables themselves: average precipitation, average temperature, annual PDSI. So here's that model, similar to the one for the numbers. We look at the log of the sage, or the growth rate, as a full PDSI. And so in this particular instance, we show a similar response pattern. And for each of those 4 areas. So what are our findings? Our basic conclusions from this statistical effort? Well, there just is very little evidence for climate cycles in Wyoming. That may not be news, but the data are pretty clear about that. Second, flood counts and population growth rates vary annually, but with no regular periodicity, i.e. there just are no cycles in them, in these responses. And the only reason we would expect that is if there were cyclic patterns in the environment or meteorological data, which there are not. Flood counts and population growth rates have a significant curvilinear relationship with PDSI. So, in other words, both extreme dry and extreme wet climate conditions promote lower flood counts and growth rates. So, that leads to what we consider what would be next steps. Well, this particular research suggests that in spite of other sources of variation over that same period of time, 1960 to 2016, climate variation has had a pronounced effect on abundance. And whether it's drought years or wet years, you could see the response in the lek behavior of these birds to those particular years. And knowing the climate variation, knowing what the climate variation is, allows us then to use a data-driven species sustainability approach. We can make decisions for the sustainability of sage grouse if we know what those climate conditions are compared to these past data. And so in addition, we can measure the regional, i.e. core area climate conditions, and that could be helpful in management decisions to ensure sustainable populations for the entire state. So core area dependent research or decision making may be important to long-term sustainability of sage grouse in the state of Wyoming. So here's kind of our follow-on recommendations. We suggest that we further explore core area specific relationships, let counts, population growth rates versus regional climate conditions. And there are specific models then that could be generated for those core areas. And you can see for E and F, for example, you could combine them and have a pooled data source and have a single model that predicts let counts for those particular areas. But the others that are disparate, we want to make sure we have a separate kind of prediction model for that. In addition, we thought about, from a standpoint of what we should expect to find, is some sort of relationship between lag time. In other words, the environmental conditions or climate conditions last year, we would think would set up what we'd expect to find in lek numbers or sage grouse abundance in the following year. That seems reasonable, but our preliminary evidence doesn't we're not sure about that. We think that needs to be further explored. And then in order to develop valuable models for having input to management decisions. And finally, we recommend incorporating climate-related patterns. Even though there's no cycles, we encourage incorporation of climate-related patterns into the Wyoming sage grouse management decisions themselves. In the end, everybody's interest is to promote the sustainability of this endemic species to the Pacific or to the Northwest and Western United States. So those are our basic recommendations. This sort of concludes our presentation. We would very much like to entertain comments, questions that you may have. Either Dr. Belk or myself.
Tom, reaction?
Yeah, a couple questions anyway. So here, you, just because this slides up, I'll hit it before it goes off the screen. You talk about core area specific relationships, but you also mentioned areas E, F, G, and H. we are on the same page that those are not the same things. The core area is not E.
Is not E.
Okay, as long as, yeah, okay.
Yeah,
I was
it's a
confused.
geographical
I thought you were
representation.
equating those two as being the same.
No, we understand, yeah.
Okay.
Core area is different.
E is a population in the land or greater South Pass
Well,
core area.
yeah,
A
it probably
subpopulation.
isn't a population, they were lines we drew on a map to create local working groups.
Right.
So, yeah.
It's a geographic representation.
Yeah. I'm sorry?
It's the entire working group for that.
Yeah, so, you're familiar with Northeast.
Yeah.
And yeah, that makes sense as a biological unit, but E and F
Yeah.
don't, I mean, it's a line across the desert. There's no topographic or barrier to birds or anything like that across there. But they're, it's reasonable to do this type of analysis. So my bigger questions, I didn't see you talk about, or hear you talk about Fady and Doherty and Fady and Aldridge. They certainly came to conclusions that these populations are cyclic.
Here in Wyoming?
I think I see why. They didn't try to go back to the scant data back in the 40s and 50s. And I would say that data is very biased, high. It's Patterson's data on the best population the planet probably ever had. So those numbers on average, plex size, are quite high. Are you familiar with those papers, first of all?
We have done an annotated bibliography, but I don't particularly recall those papers.
So I know of those papers and the data that they used. What we tried to do is to explore a little longer time period, and there are problems with the data. We didn't use data prior to 1960. There is this trend that you'll see in the front part of that data decline by about 70. And if you exclude that and look at those, our point was that if you look at each of those as individual groups, there is poor fit for a cyclic model. You can produce a model and say, here's the best cycle fit, but it's poor goodness of fit. And those cyclic patterns vary among each of those geographic areas. And so that was the basis for us saying that, and you can look at the same data and come to different conclusions, right? And we would emphasize that you can fit a model to that, but it has no basis in any climate-driven sort of thing. So and also it is you have to wrestle with the idea that goodness of fit is pretty low, and in their papers as well, right? So you can say it's cyclic or not, but you've got to justify that based on kind of how well the model fits. And if you take shorter and shorter time periods, you get a better fit, right? Just because you have less variation in total. So we are a bit at odds with what they would suggest, but I think either way what you have to say is there's not a strong cyclic signal there. And if you take some of those segments, if you look back at this slide, if you take some of those segments of time, you could come up with a stronger conclusion than what we have. But it's not even in the right-hand side of those graphs, the fit, and if you look at H, you'd think, okay, those last two curves fit pretty good, and if that's the data that we had, but those patterns are different from what you find in F and different from what you find in E. So I guess we'd be on a little bit more cautious approach than some of those other papers in the sense of a goodness of fit argument.
Yeah, I would
if
just
that makes sense.
make sure you, in whatever paper you produce, that you
That's an
articulate
excellent
these
suggestion.
differences between,
You bet.
between the papers.
So let me follow up on that with a non-mathematically driven question. One of the concerns that I think a lot of us have had is that we're trying to deal with a species today.
and we keep complicating the data by going back to when the skies were blackened by the birds and you know, all of those kind of things. If you hold that we are in a period of some climatic change, which I think we are, then isn't there value in looking at a shortened time period to see what is going on relative to generalized patterns of wet and dry? Because I think we do know that there are, whether they're cyclic or not, El Ninos, La Ninas, other patterns that fit our landscape. That seems to be more of a pertinent question today than what's happened since 1948. And I think maybe, Tom, you're kind of at the same place. We've got all this data from 48, but what does it tell us today?
One of the take homes here. Did you want to address it? One of the take homes here is that by assessing the reliability of the data and going through and agreeing that these early dates are somewhat questionable, by looking at a broader span, the question you're asking has to do with how does this species respond in an evolutionary sort of context, right? So as climate changes over long periods of time, what can we predict? And the interesting thing is, there is a signal here that links abundance to changing climate. And it doesn't seem to be particularly strong as a cycle, but just the linear change in climate, this linkage, right, we can use that to say, well, what about, given the more reliable data that we have, which is what contributes most to that linkage, what about using this to say, what if we get just a modest decline in precipitation, right? And this could either be an increased frequency of El Ninos or a lengthening of those or whatever it is. But then 50 years from now, based on that response pattern, we can start to be, as you're saying, forward looking and say, 50 years from now, this is what we're going to run into. Most of our, click back to that hump-shaped curve, most of our variation is going to be out on those tails. You got to go the other way. Yeah. Forward. And this is the part that I think I'm echoing what you're thinking there is potentially worrisome, right? If we, in a linear sort of change, in 50 years, if we spend more time on that drought side of the Palmer Drought Severity Index, then although this is a modest hump, right? It is a modest curve, but you can see that over time, on average, we're going to see a decline that is going to be driven by that link in the climate that's been identified from the historic stuff, and trying the best that we can to be reliable with that. So I think that gets it exactly where we think the utility of this is to say, not to describe what happened in the past, but to use that as a way to say, what is our likely response for some scenarios that seem to be happening and likely to happen more? Temperatures are likely to increase a bit, and drought is likely to increase. So this gives us the frequency. So this gives us an opportunity to say, here we have a proactive, predictable way of getting ahead of the curve and saying, look, we're not planning for next year, we're not planning for next decade, we're planning for 50 or 100 years out. How can we respond? What do we need to do to mitigate this sort of thing? And I think the links are sufficient that we can begin to make those and to utilize the data in that way. We'd like to, I mean, we can run some predictive future scenarios, right, in the beginning and say, what if there's just a slight decline in precipitation or a slight increase in temperature? What does that make our let counts look like 50 or 100 years from now? And now when we can still do something about that, presumably. So I think you're right on, if I understand what you're saying, I think you're right on that's the step right? That's what is both worrisome and positive about this climate linkage, right?
Yeah, I agree completely, and this, I mean, this basically validates everything a sage grouse biologist and a cattleman would say. It's either too wet or too dry.
Yeah.
We're Goldilocks.
Yeah.
We like it just right.
And this makes sense in terms of the biology of the species, right? I mean, if you think about 1 million years of selection on this species, and what can you select on? Well, you select on the average over that time period, and things that depart from that in either way, and for different reasons from the biology of the species, right? If it's too wet, you get egg clutch failures, and if it's too dry, you have poor chick survival, and those things are in the literature. So it makes sense from the biology, but it also, I think it allows us to be data-driven into the future, not just from, we think this is the way that it works, but here's a linkage that we can use.
So the next step that I would be curious about is whether or not, as a predictor, you can look at anticipated changes in growth rates to give you a benchmark to compare against. And I think one of the, we know that the populations cycle. We know there's climate variation, and in Wyoming that can be rain in one place and dry in another, okay?
Right.
But is there a way to have a predictor that says if you are in those sweet spots in the middle, that you should expect a growth response within 12 to 18%, so that if you're at 4%, you can look at other factors? Is that completely out of the realm of possibility?
No.
I'm trying to shorten the time here. Where a 10-year cycle, a 20-year cycle, what's going on? Are the populations responding to the climate in the way we would expect?
Yeah. So this particular graphic is illustrative of that very principle. We can create then, for that center portion of that graph, we can say what is the best estimate of the response, and therefore we can put a interval estimate as well as a point estimate. So you can say, well, 95% of the time it could be as large as this or as small as that in this center part of that graphic between the PDSI and the response of males per leg. So you could have a boundary of what you might expect in terms of here's the range we expect for these sorts of conditions. What's next year going to be like? Is it going to be like, we don't have to look at the farmer's almanac, but you could look at the data based on the PDSIs, and by the spring, see, in this case, it's winter PDSI that had the strongest relationship to what you would expect in the following springs, we presume. That's what we're trying to say.
I'm not surprised at that at all. But Tom, I guess what I'm trying to get at is not necessarily a predictive forward-looking model, but one that can analyze what response we had in any given year and tell us if the populations are functioning the way we would expect. I'm looking at it as a test against other factors that we may have control over. Forage quality, soil stability, sagebrush resilience, those kind of things may be having an effect that is getting clouded as noise in your data.
Right.
In other words, it should respond to a perfect climate, and it's not. Why is it not? That would be.
But I think that's an excellent way to use this as a baseline predictor, right? And you could get that year by year just using this relationship, and you can say, what's the year look like? Here's our baseline predictor, and if we depart from that, outside of those error bars, outside of that expected region, the 95% confidence interval, if you depart from that, then you've got to go back to those other things and say, what is it that's causing departure from this basic climate relationship, right? We can't control climate in that sense, but we can go back and look at those things and use this as a baseline to compare.
So the other question I have is, this cannot, I don't think, reflect the timing of heat, moisture and other things. Is that correct?
It does in the sense that we have divided that up each by season, and in some cases, one of those has a stronger fit than the other. For a predictive model, you could use multiple predictors, so you could include all those in, and in some years it might be, as the other two graphs showed, there is a strong relationship between spring in some years and fall in other variables. But all those could be included in a predictive model so that you can take out the variation, whatever it is, whatever it's due to. So it could be due to not just overall PDSI for the year. So when the
Rain versus snow.
yeah, it could, because that's precipitation pulled out at different times of year, right? And then you've got temperature pulled out at different times of year, because it may be a hot spring. We showed you the things that fit the best, but as you pointed out, every single PDSI model, so each of the seasons plus the overall, have this shape and have a fit. It's not quite as strong as this. This is the best one, but still those can be used as predictors. There's no reason that you have to have just one predictor that might then miss some of that annual timing, that seasonal timing.
The thought
We have a
occurred.
question.
Sure, okay.
We have a question on the chat. On this slide, what is the difference between log 10, 1.25 birds and 1.60 birds?
Well, what we're on the vertical axis is the logarithm, meaning it's the power. So we're taking 10 to the power of 1, which would be 10, right? 10 to the power of 2 would be 100. So if I understand the question correctly. So in between there, probably been easier if I'd actually
We could have back transformed that, but it would be so it would what was it, 1.25 to 1.5?
1.6.
1.6. So the difference there, you're talking about what, 40 birds relative to 10 as the low and 100 as the high, that would be represented by 1 and 2. So you're talking about 40 to 50 birds. That would be a difference in average, right? Something along those. I'd have to back transform it, but it's something along those lines, right? It's depending on where it's found, there about half of that range.
Yeah, between 20 and 50 birds.
20 and 50.
Mm-hmm. So here's
What's the,
And I'm getting in water above my head when I just use the word statistics, but is there a way to put an error bar on this? Is that curve meaningful?
right. What we're seeing in the curve is the best guess, or the best predictor for that given value of winter PDSI. But because of the variation in that process, we could bound it and put an upper bound and a lower bound, saying that 95% of the time that predicted value could be as large as this or as small as that in any point of the data for winter PDSI. And so we would expect then that those, we could put error bars, which we could do. I didn't choose to do it in this particular case because as preliminary evidence, I'm just trying to piece out or pull out the major response that's going on. But if we want to use the model in a predictive capacity, then we'd have to do exactly what you said. That is to look at those error bars.
Which is back to what I was
Exactly.
Yeah.
And then that becomes very useful, because things that fall outside of those predicted, the confidence intervals or the error bars or whatever they are,
Prediction interval.
things, the prediction intervals, things that fall outside of that are then things that we have to go and say, this is driven by something other than this climate pattern and the expected variation that we would find there.
Yeah.
Which kind of leads to my next question is, there's lots of variables out
Yes.
there. There's lots of weather variables, but there's lots of other variables.
Yes.
And I mean,
Exactly, and so this is useful in terms of tracking climate. There are lots of other things, but that's, in this case, you can set sort of a baseline expectation, and then when things diverge from that, you can then go looking, and there are a host of other things. Some of those are things that can be managed and some are not, right? And so this was an attempt to try to get at this idea of is there some sort of periodicity or at least predictability that comes from the climate? And you know, climate is, I mean, it's highly variable, and we were frankly quite surprised to find a relationship. Given the number of variables, this is a reasonable place to look for a baseline predictor, and then outside that you can go looking for other causes.
Did you have problems matching the area that the PDSI is based on to your EDF and G?
So we did that in a very comprehensive way, in the sense of we found the weather stations that corresponded most closely to that, and in cases where those areas were spanning more than one, we took the average of the two. And so we gathered up all of the longer term weather data that was available, but we did use sort of source averaging, so that we're not just reliant on one point predictor in most cases. Okay. Now that you know, you can only use the data that are there, and Wyoming is sparsely populated with weather stations, and so, but we did the best that we could to represent those areas. And so, for example, you're talking about the two that are just divided by a line of convenience, right? So if we had a weather station that had half of one area and half of the other, then we used that and averaged into both sides, right? So it is a little bit challenging, but we used the data to the best that we could in that sense.
My impression of this particular graphic, which is the focus of our presentation here, is that it's suggesting that of all the other sources of variability that's causing that variation around that line, and there could be like predation pressure, there's competition, there's disease, all the other factors that go into population regulation, it kind of gives you the impression that what's dominating the population growth and regulation of sage grouse is what's occurring in the climate conditions. And I mean, that includes things like hunting pressure, right? There's lots of variation associated with taking out of the population on an annual basis. And but it appears that the variety of different other factors that contribute to population regulation is just going to increase the spread of the data around that particular line. And that line is saying that what's dominating the population growth and regulation of this species is what's occurring in the climate.
So if we, I guess, kind of to follow on that a little bit, basically, if we look, you were talking about, well, what if we see, you know, slight increases in temperature or whatever, but to me, you've also got an issue if we're seeing more variability and we're spending more time on the edges of this graph than in the center. And so if we look at
in terms of recent history, you mean?
Well, just and projected for, at least for our area, so we're clear eastern Wyoming. But if you look at that and say, if those cycle times where we're spending more time on the edges become longer than the expected life of the grouse, then we're really going to see some real severe influences or potential influences on population. If we're cycling back and forth across that, and there's sometimes in that average range for the grouse that's out there and she reproduces the clutch, we're probably still okay. But boy, if it's that cycle timing, then that to me seems like it's really going to be a problem.
So you could,
potential problem.
That's exactly.
You could graph that instead of doing it by EFGH. You could do it by time stamp.
Right.
That same graph.
That's an interesting point, because it may not. I mean, this is gathering historic data, but it may be that the good times passed in the sense, and then we're spending a lot more time out on those sides. So it would be, that'd be an interesting thing to do, is to look at the year identity of each of those points.
Yes.
And this is a way of sort of refining. So Carrie made the point that we can refine this to each of those areas. This is just the overall thing. And it may be that some of those areas, you can kind of see this in the different scatter of the different colors. but it may be that some of those areas are much more prone to one side of this curve than they are the other, and it may be that the more recent times are actually accumulating in one side of this curve or the other, or I mean, hopefully they would be sort of a mix in the middle, but that's a really good point, yeah.
But there's another part of that if you look at this graph, clearly your variability is greatest in Casper.
F, yep.
Yeah, you've got green dots all over. The others appear to me to be much more resilient, particularly if you look at Lander, which is E, and Rollins, which is H. You don't have the outliers, you don't have the effect. And is that, then my question would be, is that because of the overall population density that they're more resilient? Is that weather driven? Is that other factors?
Excellent questions.
Well, yeah.
Yeah. Yeah, and that's the point of this, the follow-on of looking at this more so for each of those cores, we've identified sort of an overall pattern, but I think there's the devil in the details here, right? And it may be that it might be much more useful in the sense of saying, well, what if, when we look at those individually, then that information would be much more useful on that local area than this first relationship.
But it would also be helpful to be able to tease out how much relationship is there, because if this is the aggregated data, I'd love to see what that curve does. I mean, that almost goes flat line for the blue, but it would be a much higher arc for the green, it would appear to me, based on those data.
So we have a question that ties into this discussion from the chat. So this is from Phil Dom, who's in Pinedale. As Bob indicated, regional weather can be variable. Was the PDSI LEC model examined for different areas separately? Would the different areas have better fit with a different model, e.g. linear? And then second question is it possible, from the same person, is it possible that one of the areas is driving the fit of the curve and linear model over another relationship?
It could be, right? So that's the point that we're at here, is that if you just look at everything as a whole, it looks like this relationship fits. But once again, that the follow-on point that we made there is, it is imperative, I think, that we follow up and look at those individual things, because that the other graph that you showed there, we know these areas are responding somewhat independently, right? They certainly have different climate if you measure those. So there's no, I think that there are some of the areas that when we look at them would fit that curve, and others might be fit better by a linear, you know, it's mainly driven by drought, right? And the wet years have less of an effect, partly because in some areas, wet years are not near as common, right? And it's drought and medium years the way this would be defined. So this graph right here, by putting in both the Sage Grouse data and the climate data, you can see that we would expect E and F to behave very similarly, but those others, you're right, and I think that's patterns that need to be clarified and explored. You bet.
The more knowledge we acquire about sage grouse behavior and population growth and regulation in these different geographical areas will allow us then to make decisions in the management process that will have long-term sustainability for that species. And the end here, the reason we petitioned and proposed what we did was to support the SGIT's effort to try and keep this species from getting into the endangered species list, and to promote growth and development in this particular organism. And I think that's still on the governor's hit list. Let's go backwards again. One graphic. This particular graphic, as I mentioned before, and the question was asked in the chat room, This fit is all the data from these 4 areas combined. But we just chose these 4 areas as represented because they had the largest number of peak males per lek for the years that spanning 1960 through 2016.
Can you run that curve for each area
Yes, indeed.
individually?
That's what we're suggesting we do. Is follow-on research effort would be to choose and look at the individual. We've got how many different areas? There's WR.
And we can include the other core areas. They just weren't part of this initial.
That's right. But we can do them individually as included. But since these are the 4 largest, the pattern's likely to be preserved, except I think in that original graphic at the very beginning, you could see that there's not a whole lot going on in area A.
Well, that's Jackson. I mean, there's 12 leks, so.
Yeah.
Right. And so you can see just in this particular graphic over the sage grouse lek counts that have not been adjusted for observation effort, that you have a disparity among the areas themselves. And that's why we chose to look at E, F, G, and H.
Right, you would see variation in A if you scaled it properly.
Yeah.
You can't scale it to what's going on.
No
Reference to the others, yeah.
But we could, I mean, that could certainly be included, and that may have a slightly different strength of the drivers, right? But when you start to look at those, so our goal was to look at this overall and say, what is the strength of this overall pattern? And as it turns out, there's lots of variation among, so that would certainly be the next valuable step, right? But each of those could be included, and if they're run by themselves, then that variation that's there becomes important, right? And so when you look at them all together, then it's easy to sort of say, oh, that one's really constant, but it's just a scale issue, right?
The presumption was that with this identification of these areas A through H and WR, that thinking on the part of the wildlife management was dependent upon that particular area. And if that's true, then there is justification now for thinking about what do we know about the environmental conditions? Are there consistently different and disparate environmental conditions in some areas as opposed to others? And now managing the populations would really be important to know and have knowledge about those environmental and climate conditions for that area.
The other thing that can't be ruled out is that there may be some areas, when we look at them individually, that cycle in a reasonably predictable way. So even that, overall, just over the entire range that we considered, that doesn't seem to be useful, but that could, and you know, I mean, we'd have to go back and look at that on an individual basis, but there may be evidence for a pretty good fit of cycles on those on an individual basis that would then help us refine our prediction of that variation, right? Both in the climate variables and in the behavior of the birds and the abundance itself.
The wonderful thing about research is that it attempts to answer some questions presented up front. But regardless of the answer, there are always new questions that arise because you see things differently and have acquired new knowledge by looking at the data. And so we made some recommendations, but we're willing to entertain the things that are important to the SGIT.
So one thing that I think, because of the number of people who couldn't be here, I would like you to do is just an executive summary of this that we can get to the SIGIT that kind of goes through and includes some of the questions and comments from today.
Can you give us a copy of the presentation? Can we just take it from those, and I'll post it on the website?
Tom, do you, I mean, to me, the two take-homes, one is, yes, climate, weather, if you will, has a significant effect. The second is, that's probably not as periodic or as predictable as what some would have us believe. Although I don't think El Nino's predictable. I think we don't know year to year whether it's going to stay or go, and
it comes back.
so
But how
well,
often
it does.
comes
But
back?
is it a 5-year lag or
Right.
a 7 or 12? We don't know, but I'm a little not troubled maybe, but intrigued by the notion of looking at one or two of these more closely and being able then to use the expertise of people like Tom and others that could look at it and say, okay, why are we getting the response that we are in this area and not in that area? And that, Dave, would certainly tie to you guys as you look forward. Do you have the potential to increase those populations? What are the limiting factors in the Powder River Basin, Thunder Basin that you have to address, independent of weather? You're not going to fix weather, but is that a cover issue? What is it? And
Well, the aim, it seemed to me, is the things that you can control will only reduce the variation around that line.
if you control the correct one.
Right, if you know which ones they are. If you got knobs and levers, when you got to pull the right
can't
levers
just
and
go
turn the right
full
knobs, right? But all you're going to do is reduce the variation about that prediction line, which is not a bad thing because lower variation means higher reliability. So which you can make more reliable decisions about sustainable population.
Within the bars of what is expected, not,
And that's what gets complicated, well, not complicated, it's the trade-off for when you try to narrow in. Your trade-off is wider confidence intervals, and this is a great slide to show the effect of sample size.
Yeah.
Look at everything up to about 1985. Then, when we started expending more effort, well, that's actually pretty tight.
Yep.
There's a lot of similarity in those, especially if you looked at correlations of just ups and downs.
Sure.
Maybe not the magnitude in every one of them, but they're
The
all
pattern.
pretty much doing the same thing at the same time.
So
and
that would argue,
that's sample size right there.
Sure, and in a predictive model, you would probably want to go back and use a shorter time period, right? Because it does get around that. We got around it the best that we could. We took off some data in the beginning, but there's still, as you point out, that still may be valuable to start at 1980 instead of 1960, and go back and use that as a predictive basis because of the reduced variation.
I absolutely think that's right. Tom, whether it's 80 or 85, I think you picked the point where you had that shift in focus and say, but don't throw out the overall, because I think what I want to know is not what happens if you take 60 to 85 out, but what the difference is if you leave it in and then you take it out. I'm looking at the delta, not the one or the other. What is the delta now that we have a stronger sample size? Now that we have that in place, it has relevance. The rest has relevance, but it's significantly less.
Yeah, you're seeing things differently, and it's an exciting prospect to manipulate and manage these particular modeling efforts to see what else they can tell us. This particular point right here, for example, this is 1950 something. In F area, there's 200, average of 200 individuals per lakh. I'm not sure I believe that, but I wasn't there.
I think.
I mean, there could have been 2 lakhs. I have no idea.
Right.
I don't know.
400 individuals
How
and
many
2
were
lakhs,
looked
and the average was 200. But I saw also a PowerPoint presentation that I think either Karen sent me or somebody that was an attempt to calibrate the observer. Here's what you do: you go this time of the day, and you go only between the March and April 1st or something of that nature. The idea was an attempt to try and get all the observers to be more or less alike, so less variation in just measuring.
Yeah, there's a paper on that out of Colorado State this last year, so that they've analyzed that. That's available.
Any questions from the chat room?
No new ones.
Okay. We appreciate your time.
I think this was good. I think if you'll get that executive summary, we can have a conversation about this at the next CIGIT meeting. So
Good.
appreciate you coming all this way.
It's our privilege. We enjoyed the research effort.
Great.
Thank you.
Thanks.
Thanks everybody online.
I know you have 50 minutes before you got a truck, but